I'm Lionel Borglia with Siemens PLM Software. Today I am going to prepare a model of an hydraulic excavator for real-time applications. My presentation will be split in three parts. The first part will be the presentation of the actual model of the hydraulic excavator, the working scenario, some results, and already some tips in order to maintain the simulation time acceptable. The second step will be to present the methodology of model reduction together with the different tools that supports this methodology. And as a third step, I will explain how we can use this real-time model within LMS MSIM environment. So the first step is to present the actual model of hydraulic excavator. So what we have here, it's a full model starting from the combustion engine to the mechanisms. So the model includes the combustion engine with first level model of the engine control. All the actuation system included into the excavator, starting from the swing motor and all the hydraulic cylinder for the boom, the dipper and the bucket. All these hydraulic actuation systems are connected also with a 3D mechanism which is represented in this part of the system. In order to simulate the working scenario, we use the state chart functionality of LMS MSIM. The state chart functionality will define the different steps of the working cycle, and the working cycle will be the traditional JCMAS cycle that is used for regulation. So some results of the simulation. Here we have access to the displacement of the actuators, the hydraulic jack for the boom, the dippers and the bucket, and also the swing angle. So here we see the working scenario, including the digging phase. Then the boom is raising. At the same time, the turret rotates. So we release the bucket inside the truck and we come back to the initial position. So in order to perform this cycle, it takes 20 seconds of, let's say, of working cycle time. Let's have a look now at the CPU time. So the CPU time of the simulation, so simulating 30 seconds, takes 180 seconds of simulation, so roughly 6 times the real time. So we are 6 times slower than the real time. So now how to make this model real time? So we are going to use a first tool, which is the performance analyzer. So within the performance analyzer, we have access to the results, to some information of the solver. For example, the current integration step, and also the state contribution, meaning which part of the system are CPU time consuming. With frequency analysis, we have the possibility to visualize at what are the maximum frequency of the system, what is the maximum frequency of the system at the different CPU time. So we can see here that we have a very huge frequency, around 20 seconds, which is around 100 kilohertz. So this frequency is indeed very high, and we will try to reduce this frequency. But to reduce this frequency, we need to understand what are the components that are involved in to create, what are the components that creates this very high frequency. So once the simulation is finished, we can have a look at the results of the model projection tool. So this tool is a graphical tool that allows to show for each linearization time what are the high frequency and what are the components that are involved in this high frequency. So here we click on the maximum frequency of the system, close to 100 kilohertz, and we can see that 2 components are involved in this high frequency. And these components are 2 hydraulic chambers which are included into the dipper actuation system. What's happening at 20.4 seconds of the simulation? We see here that we have the pressures that are almost equivalent, and we have a cross-sectional area between the 2 chambers which is very high. that creates the very high frequency. So one solution could be either to reduce the size of the orifice or to increase the volumes. It's what has been done with a step 2 model, where the volume of the chambers have been increased from 2 liters to 10 liters. And as a consequence, the high frequency has been removed and the calculation time has been reduced. So now let's compare the results of the simplified model with the initial one. So first we compare the results of the simulation. So of course the modification in the parameterization should not impact the result of the simulation. So here we compare the displacement of the deeper cylinder between the initial model and the simplified model. So we see that we have limited modification in terms of results. It's up to the engineer to understand if this modification is acceptable or not. But if we look in terms of CPU time, we will see that we have a huge benefits from the modification of the volume of the chambers because here we have reduced the CPU time from 180 seconds to roughly 85 seconds. So we are almost divided more than 2 the CPU time. So step by step, we continue the analysis, still using the 2 different tools that I presented before, the performance analyzer and the model projection tool, and we can reach almost real time. The last step is to make sure that the model can run with a fixed step solver. In our case, the model is stable with a fixed step Euler fixed step solver at 0.15 milliseconds. So let's have a look at the simulation, and here you can see that definitely the CPU time is real time, almost, and the results of the simulation are in line with expectation, meaning that they are the same as the initial results. So now we have different possibility of using this real-time model. The first one can be for control unit validation. So this model can be exported to any real-time platform, DSpace, ETAS, and so on, and can be used by control engineers to validate their real ECU. Another way of using this real-time simulator is to perform human-in-the-loop simulation, meaning that we have the possibility to interact directly with the model and see the reaction of the excavator in function of the operating, in function of the sequence required by the operator. So for doing this, we can use the dashboard functionality of MSIM together with the interactive signals that can be connected with the different servo valves here of the system. So let's have a look. Let's run now the simulation, and we will interact with the model. So we set a final time of 5 minutes, for example, and then running the simulation, we have the possibility to interact with the model. So, for example, we rotate the bucket, the swing here. An output of the model here is the power that is requested by the excavator that is required to rotate, and so on. So you can have a look. We can see how the system behaves with the real mechanism. As a conclusion, I have demonstrated the capabilities of LMS MSIM to develop a real-time model of an hydraulic excavator, starting from a non-real-time model to reach real-time simulation, using the performance analyzer and the model projection tool. Now the model can be used either for human or operator interaction, or for the validation of control strategies. Thank you for watching. For more information, please visit our website.